Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to NPTEL course on groundwater, hydrology and management. This is week 6, lecture 4. In this course, we are looking at, more importantly, groundwater as a component, how it recharges, discharges, and then management. How we break in this course is until week 6, you'll look at most of the important concepts of groundwater. Then we'll jump into managing the groundwater resource. On that note, we have been looking at the groundwater recharge and discharge properties in this week's lecture. In the past couple of days lecture, we have looked at the last 3 lectures. We have looked at groundwater recharge concepts. How is it recharging? What are the different methods to recharge? And how to estimate. Let's move on and look at some more estimation methods. Groundwater recharge from seepage. Why is this very important? This forms a very important task because especially in environments where there is a water body, because a water body can influence the groundwater movement, both recharge and discharge. Okay, so in this term, we are going to look at recharge. And as I said in the previous lecture, just before the end of the lecture, I mentioned that recharge and discharge are happening through similar monitoring process, which is the water level. At what timeline it happens may be different. What is driving the recharge or discharge may be different, but monitoring is almost same because you're going to use a similar methods. Here, the physics that drives it is just opposite. Okay, for example, in a recharge, water goes in a discharge, water comes out. Okay, you push water in, that is recharge. You pump water out, that is discharge. So similarly, in a natural environment where there is a water body and a high elevation land with groundwater table, water table would flow into the stream, river, network, whatever you call it, lakes, ponds, etc. And that is groundwater recharge. Okay, into the stream, but it is a discharge for the groundwater. In this lecture, we are looking at groundwater recharge. So let's take this example where you have a land which is also at high elevation. However, the water table is at a low elevation compared to the stream. So when water comes in the stream, it tends to flow down and recharge your aquifer. So to prevent this, think of this as a canal. To prevent this, in regions like Gujarat, they put lining, which is cement, to prevent the water to recharge into the ground. They don't want it, they want to take it to the farm, which is also why they built the canal. So now coming back, depending on the use, you can make a canal recharge or just take the water. Now let's look at the recharge concept. So water is seeping into the groundwater table. You can see here water is seeping into it. It is not infiltration, it is not percolation, it is seepage. Because infiltration, percolation happens in a medium where there is pore spaces and then the water has to push through those medium and come. Whereas in seepage, it is water that is pushing water at a good table. Look at it, there is a good water level. And then it pushes itself, it seeps, leaks into the groundwater. That is groundwater recharge through seepage. So let's see how we can measure it. This is a method as given by Wanty and Winter and promoted in the USGS book So USGS has a manual for all these different things for recharge estimation, discharge estimation, for rainfall, etc. And most are used in Indian terms with slight modifications. So let's look at how recharge is estimated through seepage. So this is your sediment surface or your stream bed. Okay, right here on the stream bed, you will put the meter in. And here the meter is like a pipe with a screened interval of 3 centimeters. And that is where water can move in or out. Okay. So in this example, your potentiometric surface or the groundwater head is at a higher elevation compared to the surface. So it is this example. Okay. And what happens is, because of the potential difference, because water wants to flow from high to low potential, water would seep in from groundwater and then come out and join your surface water. And this can be monitored through the pipe here. And the pipe has some meters which actually monitors how fast water is seeping through. Okay. And the manometer is a meter which is also looking at how fast the suction happens. So suction, or how fast the water moves through this tube. And a reading is given for the velocity of water, discharge of water, etc. So these seepage meters are kind of expensive and doesn't give you the right picture all the time. Why? Because it depends on where you put it in the land. So you can put it here, you can get a different seepage. You can put it on this point, you can get different seepage, because the rocks and bedrocks are not the same everywhere. So that is why in most terms, it is just simple enough to estimate it rather than putting a meter and estimating the rare data. More or less, it gives a different flavor. The easier way to look at it is, you have a river flowing, okay, a river flowing, and you take a discharge measurement, how much water comes in the river at point A, and take a reading at point B. Okay, you have two discharge now, QA, QB. If QA is equal to QB, there is no recharge, there's no discharge, which means the water is not losing, water is not gaining. However, if A is less than B, that means water is losing into the ground, which is discharge of the stream water into the ground, which is a recharge for us. So that is the case where you have A is less than B, okay, and the subtraction of B minus A, okay, B minus A would give you the actual water which is gained in the stream because of groundwater coming into the river. This is a discharge. If you want to recharge, A is greater than B. Okay. If A is greater than B, what is happening? Water is losing into the groundwater, which means groundwater is getting recharged. So A minus B is the total volume lost by the river but gained by the groundwater. And that gaining is groundwater recharge. Okay. For groundwater discharge, how do you do? Let's take a system where the water is coming in. Groundwater is giving water into the river. So A is less than B, or B is greater than A. B minus A is the net volume of water recharged because of this length on a non-rainy day. So all these equations should apply on a no rainy day, because if rain is happening, then water is just picking up because of rain. So you need to take it in a non-raining day. Okay. So here we can estimate the actual groundwater recharge just looking at two sections in a river and see the connection of how the water is recharging or discharging the groundwater aquifer. Again, a lot of people don't actually do these. They just estimate it because it's a lot of data. It's not one point data you have to take. You have to take multiple data. What they do, they go on the riverbed, they look at the river's material, the riverbed material, and then they estimate a value. And the other easiest way, which is really, in some ways is okay, is they say, for example, this is the river. They say groundwater is giving into in this location and groundwater is giving out into this location, which means QA, or here let's say G for groundwater. So GA, which comes into the river, is equal to GB, which leaves the river. So GA is equal to GB, no changes. The river is neither gaining or losing in the long run, which is a good estimate, one would say. So you can see how estimations and assumptions can make your life easy in terms of groundwater recharge. And you're not that particular about groundwater recharge happening along the river, because your lands are away from the river, or your house for the water level is away. So it's more on how you want to use your recharge. However, so now here comes the tricky part. What if no data is there? No meters, no money for meters, no time, and no budget, which is money put on the meters. If nothing is there, what happens? This is a concerning part, which is crippling a lot of places, because India is the most highest groundwater user in the world. However, if you look at monitoring per centimeter area of your map, or let's say per kilometer area, it is not much. It's very less compared to the other countries that are actually monitoring groundwater pretty well. So here's where we are in this situation. What if no data exists? And again, think about only 4 months we are monitoring. What if no data exists? No meters are there in some locations, and budget is less to augment or add meters. What do? You simply, GSE has given you that option also, that you can simply estimate the recharge from rainfall, because rainfall for sure you'll have. And these satellite products have given you a lot of rainfall data for a lot of years, at least 1857 till date. So around 150 years of data you have for rainfall. And you know the soil material, the rock material, because those don't change. You can use the GSI, Geological Survey of India maps. All these are in my slides. Please go and look at these maps. And when I'm teaching the groundwater data, I will show you how to take rainfall data. So what you'll do is, you can see that your recharge happens as a function of your rainfall. So this is the simple logical hypothesis given by JEC. JE says your rainfall is what is recharging your groundwater. Let's put a percentage. A percentage of the rainfall goes in. And based on the physical setting of the aquifer, the land surface, the land cover, etc., and the rainfall, you can estimate how much is your recharge. Again, let's do this exercise. They have divided India into two major hard rock formations, or rock formations. One is hard rock and the other is alluvial. Alluvial takes around 20 to 30% of the land, whereas the remaining is mostly hard rock aquifers. So the alluvial are mostly in the river delta regions, belts, etc., Ganges, Kaveri, Narmada, Tati, Pennar, etc. So those regions have alluvial sediments and formations. And of that, Indo-Gangetic has the major formations, because it is big and the river flows every day, every year. So it brings a lot of sediments, and still it's a young river, because it maneuvers, it cuts through, and also brings a lot of sediments which form the alluvial aquifers. So they say that if there is rainfall, say for example 100 mm rainfall, 22% of that is your recharge. In the previous example, we looked at infiltration. If you don't know the rock material, it is going to be very hard. So you have to know the rock material, which is found by the map. If you all you have to know is the location. For example, if I say Mumbai or Chennai, I go to the map, I look at the alluvial or hard rock area type, what is the rock type, and then I look at the rainfall and then I can estimate. In the last lecture, we looked at what is the infiltration rate. Okay. Infiltration rate is different, recharge is different, because infiltration is the water going into the ground and then plants take it, soil take it, and then still further water has to move down. So you see that infiltration percentage from rainfall is much bigger than your recharge from rainfall, because recharge groundwater still has to move further and after plant uptake, soil uptake, etc. So let's look at some examples. So you have the Indo-Gangetic and inland areas. Suppose 100 mm rainfall. So for example, in the Indo-Gangetic, you have 1500 mm rainfall. 22% of that, the recommend value, is recharging into the groundwater. So if you have your rainfall as millimeters, you can have your recharge is also millimeters. So 100 mm rainfall gives you 22 millimeters of recharge. What happens to the rest? It goes as ET and surface runoff. Then you have the east coast and west coast. As I said, along the east and west, you have a lot of rivers actually flowing out, and those are alluvial aquifers, like Kaveri, the Pennar on the east coast. On the west coast, you have Narmada, Tapti, and other rivers. The hard rock are the central part of India. And you could see that there is a lot of these multiple types, whether granite, granulite, vascular, whether basalt, laterite, etc. And depending on the rock type, there is a fracture percentage. All this has been done by GSI and other studies across the world. And they have estimated how much infiltration happens and how much of that goes further into groundwater recharge. And this is the value. Okay, so 11% of the rainfall, 8% of the rainfall, etc. So now I'm giving you the volume, but what is the time? That is hard to tell. So I can say, I give you 100 mm rainfall in an alluvial aquifer, you get 22 mm as recharge. But is it going to happen the next day the rainfall happens? No, because it is a process which takes slow time to go in. So it is better to say annual. Annually, Kolkata in the Ganges Basin gets 100 mm rainfall, for example. It takes much more. And it gets around 22% of the annual rainfall, which is 22 millimeters of recharge from rainfall in a year. So that is a good way to tell. You cannot say that tomorrow there is rain, the day after tomorrow it will be recharged. No. So if I take 100 mm rainfall today I'm getting 100 mm rainfall, which is like a flood. Does that mean tomorrow I'll get 88% as runoff and 22%, which is 22 mm in my groundwater recharge? Not. It will take some more time. Okay. So please think this out, and when you discuss this with others, make sure there's a time aspect, and the time no one can tell, only you would be able to estimate it. But again, at the end of the day, they want annual recharge. If you look at the last lecture I gave, the Groundwater Board has given you recharge annually. Okay, so take annually, that is fine. But for understanding the physical process, you need to understand that it is not a daily process. It takes time. And the last part I would like to say, after we did the estimations through water budgets, through your meters, seepage meters, etc., and water level fluctuations, the last part is models. Multiple models that can easily estimate your groundwater recharge based on the driving factors, which is your land use, land cover, your rainfall, the type of aquifer or the type of rock, soil, etc. And those can be taken from these open source models. So the link I'm giving here in the bottom, if you just go there, all these models are already there. and you can click on the title and it goes into the model where you can learn it for free. Okay. So it is very important that these models have their own positives and negatives. You can look at the rate, and there are multiple models for a single parameter, which is groundwater recharge. Please understand that it is because of the changes in the modeling world, because the computers have become faster, the data has become more accessible. You see more models coming up every couple of years once. So you have around 1988s, there's a model, and then there's some new models in 2002, etc. So you have to read about these models, the suitability for your research area, and then you pick and choose your research model. Now someone can ask me, which is the best model? As a faculty, what do you teach? I would say the best model for groundwater as an open source and widely used is ModFlow. It runs on Darcy's law, which we have already explained. And it is a very simple model, less data intensive. However, it has been very successful in getting groundwater estimates across the world, not only in US or India, wherever the groundwater extraction is happening, but most of the studies have used SmartFlow, whereas some have actually gone out or outdated, etc. Some of the models. SWOT is a recharge estimation model, not a groundwater model, but it is a very good surface water model. So surface water, you have rainfall converting to runoff and then infiltration. After infiltration, it goes into recharge where ModFlow comes in. MODFLOW, this one. Sutra is also a good model, but ModFlow is widely known as a very good model. It's a 3D model also. We will see some of these models, how to set it up, etc. in the class. So now we have looked at recharge estimates and how to do recharge, etc. What are the different methods? And then we came to models. But the important question is net groundwater recharge enough? Okay, what is your net groundwater recharge? So this is your time on your x-axis, and then your on y-axis you have your H, which is hydraulic head. Okay, let's do Jan to December. Normally you do water year, which means at least here in monsoon starts in June. So I'll do June to June, but let's do calendar because most of you would like to have calendar year. So the water would start around here and then come down during your summer and then rise up during your monsoon and then come back to the same value. Okay. So if this is happening, the downfall of the water level is because of discharge and pumping, etc. And then your recharge happens because of monsoon. Okay. What is net? Net is not only the groundwater recharge happening through your rainfall, but also the seepage, the dams, etc. And you have to also calculate your water used, because that is also being taken from your net groundwater recharge. Correct. It has been taken for your agriculture, but it is taken from a recharged well. So that is what net recharge is. So you have to take it from here. So from here, the recharge is happening. You cannot say that, oh, no, I'll start here because I don't take into consider the water I used for agriculture, etc. So you have to take from this and also include the water that you have taken out for recharge and groundwater irrigation, etc. So it is very important to understand that net groundwater recharge. Is it enough? Is it stable? Is the question. And as you know, as we spoke, the groundwater use has always been increasing in India. So definitely the groundwater recharge is not enough. It is going down. The rainfall patterns have changed, the climate patterns have changed, and you see that pre-monsoon level, which is before your monsoon, which is from your peak monsoon to your next monsoon, the water that you've used in summertime. If you look at it, it is a drastic condition. Most regions are red in comparisons from 2014 to 2016. The index is the same, the colors are the same. So what it means is those areas which were green, having healthy groundwater levels of 2 to 5. So within 2 to 5 meters, you'll have groundwater. All those are changing into yellow and pink and red, which is not sustainable in the long run. So it is very important to do more groundwater recharge. So here's the question. Is it possible to do more groundwater recharge? Because rainfall patterns are changing. Naturally, it is not going to be enough. Okay. And that is why there are a lot of schemes. Just look at the central part of India. Yeah, this red part where Rajasthan and Punjab, Haryana, those regions, you have a lot of groundwater use, a lot of agricultural activities. But look at central India, so where the hard rock aquifers are, there's so much water used, and that is why it shows a big drop in the pre-monsoon level. So the net recharge is not enough. Okay, or you're using more water, even though the rainfall is same, you may be using too much of water, so the net recharge is not enough. And as I said, with climate change within even a couple of years, you're seeing the groundwater available for irrigation is being unsustainably used, and your rainfall is giving less into the recharge because faster rainfall is coming, flash floods are coming. So all this has to be accounted for in the groundwater management. Let's look at the situation of the number of blocks that have been turned as critical or semi-critical. Overexploited means you are exploiting more than 100% of the groundwater that is recharged. Okay, and critical is somewhere around your 100%, 70 to 100%, and 70% semi-critical. Below that, it is safe. So what do you recommend now? So in India, is it safe? Yes, because of the water level. If you look at India level, what it was 62%. Okay, of 433 billion cubic meters, you're using 245 billion cubic meters as per CGWB. It is outdated, but still it's okay. It is a 62% use of groundwater in the country, which is fine, they said. Okay, it is safe. However, if you look at certain blocks, it is really bad. And it is in the overexploited condition. And that is why it is important to artificially recharge groundwater. I'll continue with these methods in the next class, but let me give you an introduction to what is artificial recharge. As the name suggests, artificial means it is not natural, meaning it will take more time for the groundwater to go in within a natural setting. And that cannot be sustained for the life forms, agriculture in the current India. You need to push methods that can augment groundwater and increase groundwater recharge. And luckily, the GEC, the Groundwater Estimation Committee, and the Groundwater Board, the Central Groundwater Board, have made these kind of very useful documents with live examples. You could see here pictures of examples from study areas on how you could increase the groundwater recharge using artificial means. Anything you construct on land is artificial because it is not natural recharge. Okay. In the next class, I will start with the introduction of natural recharge versus artificial recharge. And then we'll look at some examples and wrap up week 6. With this, I conclude today's lecture. Thank you.